Okay, so lecture 10 is bases. So in this lecture, we'll say that subspace is a span. So every subspace is actually a span of vectors. Define what a basis is and think about bases as coordinate axes. So a subspace is a set of vectors including 0 which is closed under addition of vectors and scalar multiplication. Okay, so how do we show that every subspace is actually a span? And this is why we're interested in spans. Well, if we take we'll call the subspace V because I need a name for it. If V is just the vector 0, then we're done because it's a span of just the 0 vector. Okay, if not, right, then there's some non-zero vector in my subspace. That's in your subspace, and then if my subspace equals the span of that vector, we're done. Else, we can pick a vector that's not in the span of V1. So pick V2, not in span of V1. What that means is that V2 and V1 are literally independent, right? V2 does not equal K V1 for any value of K, or KV1, K1 V1 plus K2 V2 does not equal 0. Oh, equals 0 means that K1 equals 0 or K2 equals 0, which means they're literally independent. That's an arrow, right? Because if there was a K1 and a K2, so that this equation here held, then that means I could move the V2 over to the other side, divide by K2, and then I would have V2 in the span of that. So if V2 is not in the span of V1, then V2 and V1 are literally independent, which is nice. So pick V2 not in the span of V1. Now, if my vector subspace equals the span of V1 and V2, then done. Else, pick V3 not in span of V1 and V2, which means that V3, V1, and V2 are all linearly independent. If V equals span of V1, V2, V3, then done. Else, pick a V4, dot, 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 dot. Since we're in a finite dimensional space, we'll eventually run out of vectors. And what do we get? The process gives us the first time we get V equals the span of a collection of vectors. What do we get? We have V is the span of a collection of linearly independent vectors. And that is what a basis is. So a basis for a vector space or a subspace is a set of linearly independent vectors whose span is the entire space, subspace. And so what we've seen here is that every finite dimensional vector space or subspace, has a basis, and the dimension of vector space or subspace is the number of vectors in the basis. That's the technical definition. That definition extends to infinite dimensions, and if you have an infinite dimensional basis, then you have the number of vectors is infinity. Okay, so here's some standard vectors. I and j are called the standard basis for R2. If you think about them, here's my x-axis, here's my y-axis. I is this vector, and j is that vector. So what's the span of I? The span of I is usually called the x-axis. And the span of j, right, that's all multiples of j, is usually called the y-axis. Is ij a basis for two-dimensional space? Well, that's asking, given a vector AB in two-dimensional space, are there two numbers k1, k2, so k1i plus k2j equals my vector AB? And the answer is, well, yeah, of course, right? k1i plus k2j is k1 0 plus 0 k2. It's a 0, not a 6. If I need that, if I add those together and I need that to be equal to a comma b, then we just set a equal to k1, the x coordinate, and b equal to k2. So here's my vector AB. A times I plus b times j gives me the vector AB. Right, so that's the standard basis for two dimensions. And in three dimensions, which would be badly drawn, right? Here's my x-axis, my y-axis, my z-axis. I points along the x-axis, j points along the y-axis, and k points along the z-axis. So the span of I is the x-axis, the span of j is the y-axis, the span of k is the z-axis. And this is a basis for three-dimensional space because any three-dimensional vector is a times 1, 0, 0 plus b times 0, 1, 0 plus c times 0, 0, 1. Any three-dimensional vector is a linear combination of these three vectors. And these are called the standard basis in three dimensions. So note that this I here is different from the I in example 2 because this is a three-dimensional I rather than a two-dimensional I. And j is a three-dimensional j, not a two-dimensional j. And so if we think about these two basis vectors, I and j in three dimensions, I is this vector that points along the x-axis, j is this vector that points along the y-axis. We only have two of them and we're in a three-dimensional space. So the span of the two is the xy plane. But keep in mind that there's a third dimension, right, that's covered by k. So in general, two vectors in 3 dimensions will give you a plane and not the entire space. So what's the span of these 4 vectors? So we're in 3-dimensional space because our vectors only have 3 components. Right? At least one of them is a linear combination of the others. And why do we know that? We know that because I've got 4 vectors, 1, 2, 3, 4, but only 3 entries in each vector. And so that means I'll have a parameter if I try to check them out. So V4 looks kind of tedious because it's got lots of big numbers in it. So we will look at just V1, V2, V3, because it's the most number of vectors that could be linearly independent. So I can put my vectors, when I'm testing for linear independence, I can put the vectors into the matrix in whatever order I want. So I'm going to start with 4, 0, 0, and then I'll put in the vector 1, 1, 1. So this is V2, V3, and then V1 is 3, minus 1, 1. And I do that because I know that I'm going to try and reduce this matrix. Why is there a minus 1? There should be another minus 1 here. I'm going to try and reduce that matrix to see if they're linearly independent. And you can see really quickly that the very first thing we'll do is we'll subtract the second row from the third row. And get 0, 0, 0 there. What does that tell us? Well, if we continue to reduce this, we get a parameter here. Right? Because the best we can do is get 1, 1, 0, 0, 1, and then we'll have numbers there. And in fact, we will get 1, 0, 0, 1 in this upper right-hand corner, and then get a parameter there. So just by looking at it here, we can tell now that we will have only 2 of these vectors are linearly independent. And the third is a linear combination of the other 2. And so we'll just pick 2 of them. And I'll pick V2 and V3 because they're easiest to deal with. So the span of V2, V3 is equal to the span of all 4 of them. And so if I can just see what the span of V2 and V3 looks like, then I can, then that's a basis. V2, V3 is a basis for that span, and I can see what it looks like. So what I'm going to do is go to, as I can find it, we'll go to Geogebra, and we'll see if the 3D calculator is actually working today. So I have a vector which is 4, 0, 0. Oops, that didn't work. Vector 4, 0, 0. And then it didn't like that. Let's try this again. Okay, so we did get this figured out. So we put in a point A, 4, 0, 0, that's down here. B, 1, 1, 1, that's there. And then the vector from the origin to B and the origin to A. So there's my 3-dimensional thing. let's see, here B is above. A is right on the x-axis, B points up into space a little bit. So I guess if I put the x-axis there, then B is sort of pointing towards us. So the red line is the x-axis. Okay, so what is the span of this? Well, we'll define a thing R, and then we'll look at right? So this should give me, that's the span of the vector A. We will scroll out a little bit so we can see it better, right? The span of the vector A is just the x-axis. So we can stop there. And so we can say S is a slider, and then we can say vector S times B. And then that gives me the span of B is along that line. Great. So let's bring this, we'll leave those both there. Hide both of these for the moment. So if I take all linear combinations of these two vectors A and B, what do I get? So just take, let's see, what do they call this? Vector W is in the span of A, vector A is in the span of that. So we'll just do W plus A is that vector. So as I change R, and this is changing vectors along the x-axis, we get this vector. If I change S, which is changing vectors along this thing, then we get these various vectors. So where are all those vectors? What's the space in which all those vectors lie? And we can take a plane that goes through the origin, goes through the point A, goes to the point B. So there's a plane in 3 dimensions. And if I think about linear combinations of the vectors A and B, that's what this long black arrow is. And as I change R and S, what do I get? I get vectors that lie in that plane. So we can change them at the same time. If we look at the plane edge on, if I can do that, I should stop this because it's making the there we go. If we look at the plane edge on and we start looking at these things, right? The vectors are always on the same plane, which we can't see because it's sort of edge on, right? But they're in the same plane as the vectors A and B as we let this long vector move around. And so there's our plane that is the span of our 2 vectors. A and B are our linear, A and B are the basis for that span, for that plane. So one of the other vectors we had was the vector 3, let's say 3 comma minus 1 comma minus 1, I think was one of the other vectors. Was it that? 3 minus 1, 1. That's that vector there. This vector D right here. If you see that vector actually lies on this plane as well. So the vector 3 minus 1 is a linear combination of A and B, and so is included in the span. And the fourth vector, which was what, 11 minus 5, also lies on this plane. Okay, so we go back to our lecture notes. Don't know why that scrolled all the way up to the top. So the span of V2, V3 is a plane in 2 dimensions. Oh, is a plane, a 2-dimensional plane in 3 dimensions. Okay. So basis is coordinate axis. V1, V2, show that these two are basis for 2-dimensional space. We've shown before, and we know geometrically, that these two are linearly independent. And what that means is that if we start with the matrix 1, 2, minus 2, 2, and 0, 0 here, then that will eventually reduce to 1, 0, 0, 1, 0, 0, right? And so that's linearly independent. So the linearly independent, there's 2 of them in 2-dimensional space. So that should mean that every vector can be written as a linear combination of these two. How do we do that? Well, if W equals AB, I suppose technically it should be R there, K1 and K2 with K1 V1 plus K2 V2 equal to W. We know how to write these kind of vector equations again as augmented matrices. Or if we take this augmented matrix, right, this vector equation turns into the question is, does this augmented matrix have the solution? We already know because these are linearly independent, if we reduce this, we'll get 1, 0, 0, 1, and some number here and some number here. And so there is a solution. In fact, it's K1 equals whatever this number is, and K2 equals whatever that number is. So no matter what W we pick, we can always find a K1 and a K2, so that K1 V1 plus K2 V2 equals W. So they span the entire 2-dimensional space. So it's a basis. So every W is a linear combination of V1 and V2. So for example, find K1 and K2, so that K1 V1 plus K2 V2 equals 17, 4. That means solving the equation 1, 2, that's V1, minus 2, 2. Solve K1 V1 plus K2 V2 equals 17, 4. And that's means reducing this augmented matrix, which isn't too bad. I'll divide the bottom row by 2. And then I'll replace the bottom row by taking the bottom row minus the top row. So we'll leave the top row alone, and then we'll subtract the top row from the bottom row. 1 minus 1 is 0. 1 minus minus 2 is 3. And 2 minus 17 is minus 15. Then I can divide the bottom row by 3. Get that. Multiply the bottom row by 2. and then add the top row. Oops, this is supposed to be a 1. Add the top row to the, add the bottom row to the top row to clear out that -2. So I get 1, 0, 10 plus minus 17 is 7. 17 minus 10 is 7. And then I'll divide the bottom row by 5 again. So K1 equals 7. K2 equals -5. So we can actually think about this in terms of, here's our vectors v1 and our vector v2. There's a v1 axis defined by that line and a v2 axis, just like we have an x-axis and a y-axis defined by that line. The vector 17, 4 is over here somewhere. And we can think of that as being K2, K1, which is 7 times V1, and then -5 times K1 equals 7, and K2 equals -5, as being coordinates, right? So 7 K1 minus 5 K2, that gives me the vector 17, 4. And so we can think of this as being a V1 axis and a V2 axis, and instead of the coordinate 17, 4, which is related to the x-axis and the y-axis, we get the coordinates 7 minus 5, which are related to a V1 axis and a V2 axis. So if we go to, let's see, back to GeoGebra, right? Here's 2 vectors. The black vector is B, the red vector is C. Here's another vector A. Is that vector a linear combination of B and C? Well, sure, we can build, oops, not that vector, I want this vector, and I want another vector, that vector, right? So a linear combination of the red vector and the black vector get me to the blue vector if I add those together. If we throw in the rest of the diagram, get this and that. So there's our diagram. And we can move this point around. This is the same sort of thing. I can say that any point in the plane is a linear combination of the vector C and the vector B by this kind of a diagram. But if we think about what we're doing here, let's see, we'll get rid of that one, and I want the other black one out. It's hanging out in space to go away. There we go. If we think about what we're doing here, right, we've got a vector B, and the vector B defines an axis, and the vector C defines an axis. We want to get to the point A. Well, go this many units along the black axis and this many units along the red axis, and that gets you to the point A. Right? So it's the same kind of construction that you see with the x-axis and the y-axis, right? Go along one line until you get to sort of underneath it, and then go up the other one. And so we can think of a basis as basically providing coordinate axis for our vector space. And that's what our basis does for us. So back to our lecture notes, and then, so basis works as a coordinate axis. Each vector in the basis is gives you a line, and that line you can think of as being like an x-axis or a y-axis. So here's a case where we saw that all upper triangular 3x3 matrices, right? And that's matrices that look like this. There's subspace of the vector space of 3x3 matrices. What's the basis? Well, every vector, every matrix of this form can be rewritten if we think about the numbers that we have like this. right? So those are three matrices. Call this M1, M2, M3. And the span of those three gives me all upper triangular 3x3 matrices. So it spans it. Are they linearly independent? Well, yeah, because a constant times M1 plus a constant times M2, for example, you can't write M1 and M2 as linear combinations of each other because the ones are in different places. So they are linearly independent. So it is a basis. And it's a three-dimensional subspace because we've got these three matrices as the basis. So you could, if you wanted, plot this in three-dimensional space, like with an x-axis, a y-axis, and a z-axis, with A, B, C as your three coordinates. And sometimes that's a useful thing to do with matrices, is think of them as points in space. Okay, so